So hello everyone and welcome to this next lecture. So in the previous lecture we had concluded the buck-boost converter. We had done the open loop control of the buck-boost converter in a manner very similar to the boost converter and the buck converter before that. So in this lecture I'm going to get started with the next converter topology, which is the Chook converter. So let me go back to the simulation library and list out the three converters we've done so far. That is the buck converter, the boost converter and the buck-boost converter. So now let's create a new simulation and let's call it the Chook converter. So it's actually the Chook converter and there is, I believe, an apostrophe over the U. I can't do it here because I have just the normal English keyboard. And let's just paste it back here. Time duration can be remain 1. Only thing I'm going to do is I'm going to decrease the time step of data storage to be the same as integration time step. The output data file can be the same and we don't have to slice the output file. Now we come to the directory. So for this, let's go over to my file browser and let me create a new folder called Chook converter. So we are now here. So let me go and open my latest circuit schematic, which is the buck-boost converter, and let me save this file in this new folder. So let me do a save as, go to the new folder I just created and save this converter. So most important, make sure you save it as a CSV file. And we'll just display this warning. That's perfectly okay. So now that we have saved this file, in this lecture, I'm going to just create the schematic for this one. That's it. That's all I'm going to do. So the question is, how does it work? In the Chook converter, in the buck-boost converter, we had used a switch in the series direction which charges an inductor. So as I said before, when the switch is turned on, the inductor is charged, and when the switch is turned off, the inductor freewheels through the capacitor. Now, the Chook converter is a kind of a combination of the boost converter and adds another stage to it. So let me be a little more explicit here. What actually happens is, let me cut out the switch S1 and let me cut out the ammeter. Actually, the ammeter can stay. The inductor goes into the position of the switch, and along with the inductor we should also add the resistor. So let's do that. And of course the ammeter L1 can also get added to this one. I believe I jumped out of view. Yeah. So the inductor is in the series path with respect to the input voltage. The switch, however, is in the parallel path. So it is in the path similar to the boost converter. If you remember the boost converter, this is exactly how it was, where the switch, when you turn it on, the inductor is charged, and the switch is turned off, the inductor then discharges through the rest of the circuit. Now, here in the Chook converter, there is a difference. In the series path here, instead of just having a diode or the inductor, here we have another capacitor. So let me cut the ammeter out and cut the diode out, and here I will put a capacitor and I will call this capacitor C1. And of course, since we have a capacitor, we should have a resistor as well. Let's call this resistor C1. And let's also measure the current here, so let's call this ammeter C1. So now this is the series path where we have another capacitor in the forward path after the switch. Now, after this again, we don't directly have the output. We have another stage altogether. So it's kind of a multi-stage inverter. So what I'm going to do, I'm going to add some columns. It's always best to give as much space as possible so that you can add several features. So therefore, let me just put wire and let me just put it all the way. and let me just pull it all the way. Good. So we have a series path. We can insert elements soon. Now here, instead of just having the usual output, we have a diode. So let's call this diode D1. Alright, actually I didn't have to do this, I already had the diode, but anyway, I'll just cut the diode out here and place it here. So let me delete this. So we have a diode in the series path. Oh my god, let me just delete this. And so we have a capacitor and we have a diode in the series path. Now there's one thing here. Technically you might think this is all we need, but remember something. You have a capacitor here and we have a switch. Therefore, we cannot leave the output capacitor as it is. Remember, if you look at this path here, alright, this is a closed path. That is, this capacitor C1, the switch S, and the capacitor C out. This is a closed path, and this closed path has only a negligible resistance. This resistor C1 and this resistor C out are parasitic resistances of the capacitor. They cannot block current, which means we cannot leave this path as it is, because this capacitor and this capacitor have literally very little impedance between them. So it's like connecting two voltage sources in parallel, and these two voltage sources need not be equal. So therefore there must be some kind of a current blocking between them. So we have another energy storage device, and that is another inductor. So we will call this inductor L2. And there is a special property about this inductor which will become evident when we simulate it, because then you will see that this inductor L2 and this inductor L1 actually have a current ripple that is very similar, and because of which they can be wound on the same core, but that comes later when we actually see the simulation result. For now, let me just put another ammeter, L2. So this is the Cooke converter. So let's just go through it. We have the inductor in series with the voltage source. We have a switch. So when the switch is turned on, as is obvious, this voltage source will charge the inductor through this closed path, because remember, once the switch is closed, this voltage source will only charge the inductor through this closed path, because that is the path of least resistance. Now initially this is all that happens. Once the switch is turned off, this current through the inductor has to flow somewhere. So it will now flow through the capacitor and through the diode. This diode is connected in such a way that the cathode is pointing downwards. So the current will flow downwards. Alright, the current will flow downwards because the cathode of the diode is downwards. So this inductor will charge the capacitor through the diode. Alright, now when the switch is turned on again, the inductor charges as always, but now the capacitor will also discharge through the switch, because remember, once the capacitor has some charge, the capacitor will also find a way to flow. That means it will flow through the switch S1. So the capacitor is going to discharge through this switch and will start charging the inductor and the output capacitor. Alright, so eventually in steady state there are basically two states of conduction. That is, when the switch is on, the inductor is being charged by this input, the capacitor is discharging through the switch, and it is charging the inductor and the capacitor, output capacitor. When the switch is turned off, the inductor, input inductor, charges the capacitor and it flows through the diode. At the same time, the output inductor freewheels through the capacitor and through the diode. So this is like a multi-stage converter where the capacitor C1 plays like a kind of a decoupling effect between the input and the output. It takes energy from the input and it provides energy to the output. There is no direct link between the input and the output. That's something you will notice in this converter. The input and the output are not directly connected, but the connection happens through this capacitor C1, which forms like an energy decoupling capacitor. So at this point of time, once we've done this, I would like to stop this lecture because the capacitor, the Cooke converter will take quite some time to edit parameters. So I will stop this for now. I will just add this circuit to the files. What I'm going to do, go to my circuit simulator, go to my file browser rather, and go to properties and select this directory, which is the parent path, and paste it here. So I'll save the simulation parameters, and you see simulation parameters have been saved. So which means that now we are good to go. We can go back and add the circuits files in the next lecture. So with this, I'm going to stop this lecture right now, and in the next lecture we will add the circuit schematic and we will edit the circuit parameters. So if you have any doubts, please do post in the comments or email me or message me on social media, whichever is your preference. Or I will see you in the next week, in the next lecture in the next week, where we will continue with this. Thank you so much and goodbye for now.